show by the principle of mathematical induction that for all values of n belonging to the set of natural numbers, the following equation is true. Okay, let us begin. So our first task will be to convert the given equation into a mathematical statement. So for this, what we'll do, we're going to consider Pn. So let us suppose that Pn be a statement which is given by P of n such that we have a plus d added to a plus 2d going all the way up to the last term, which is the nth term, a plus n minus 1 times d, and it's given here that this sum equals to n over 2. It's actually not n over 3, it's n over 2 multiplied to square 2 times a plus n minus 1 times the common difference d. Fine. So this is a statement. So what we have done is we have converted the given equation into a statement, and we need to verify that this is a correct statement for all values of n belonging to n. It simply means that any natural number that we choose, it always has to be a true statement. So how do we do that? So let's check for the first natural number, n equals to 1. So for n equals to 1, the statement is now going to become P of 1. Now since we're considering n equals to 1, that means we're only considering the first term in the series, where we have a on the left hand side, but on the right hand side what we'll do, we'll replace the n value with 1. So that's going to give us 1 over 2 multiplied to 2 times a plus n minus 1. So that's simply 0 times d. So that means we have a equals to 2a over 2. That all gives us a, which means that this simply means that the statement P of n, this is a true statement. This particular statement is true, but holds true only for n equals to 1. Only for n equals to 1. Now, in order to prove that the statement equally holds true for other natural numbers, we are going to make an assumption here. We are going to presuppose that P of m, let P of m be true. Now, if P of m be true, so this simply means that for the statement P of m, this is now going to be rewritten as a plus d plus a plus 2d going all the way up to the last term. But here, this time the last term is going to be denoted by a plus m minus 1 times d. Fine. So this is going to be equals to m over 2 multiplied to 2 times a plus m minus 1 times the common difference d. So we are saying that the Pm is a true statement where m is a natural number. So we need to specify that where m belongs to the set of natural numbers. Fine. Now, if Pm is true, then we are going to check whether if its next consecutive natural number, that which is m plus 1, if it is true or not. In other words, here our goal will be to verify that the statement P of m plus 1 is true. This also holds true. Meaning, in essence, we have to show that P of m plus 1, the statement is going to be such that we have a plus d, that's the second term, going all the way up to a plus m minus 1 times d. But since we're considering m plus 1, so when we replace m with m plus 1, that's going to give us the last term, which is going to be a plus m times d. And this should be equals to m plus 1 divided by 2 multiplied to 2 times a plus m times d. So this is what we have to prove. How do we prove that? So here what we'll do, we will start from the left hand side. Now on the left hand side of our statement of Pm plus 1, we have a added to a plus d going all the way up to, we have a plus m minus 1 times d, and then we have the next term, which is a plus m d. Fine. Now what we will do here, we'll take the first term and the sum up to the second last term, and we're going to replace this with m over 2 times 2a plus m minus 1 times d. The reason why we can do that is because we have assumed that Pm is a true statement. P of m is a true statement. So let's replace this with m over 2 multiplied to 2 times a plus m minus 1 times d added to a plus m times d. Fine. Now what we'll have to do is combine both of them. So let's do one thing. Let's take half as the common factor. So we have half multiplied to, now we have m times 2a, so that's going to be 2 times am added to, we have m minus 1 times d, that's getting multiplied to m, so we have m squared d minus m times d added to, now from a plus md we have taken half as the common factor, so that is going to become 2a added to 2 times md. Fine. So that's going to be equals to 1 over 2 multiplied to 2 times am added to m squared times d. Now negative md added to positive 2md makes it positive m times d added to 2 times a. Fine. Now what we'll do, we are going to combine two terms at a time within the parentheses. So if we take 2a as the common factor from the first term and the second term, we have 2 times a multiplied to m plus 1 added to. Next, we are going to combine the second and the third term by taking m times d as the common factor. So that means it will get multiplied to m plus 1. Now from both of the two terms, we can factor out m plus 1. So we have half multiplied to m plus 1 multiplied to 2a plus md, and this is exactly the expression on the right hand side, and we can verify it. We have half m plus 1 times 2a plus md. We have half m plus 1 times 2a plus md. So we have verified that the statement p of m plus 1 is a true statement. So we will mention that since the left hand side of the statement equals the right hand side, so this simply tells us that the statement p of m plus 1, this particular statement is a true statement. So this is going to be true. And now we can generalize it. So hence we can say that p of n, this is also a true statement. So this is a true statement and it's going to hold for all natural numbers. Or we can say this is a statement true for all values of n, for all values of n belonging to the set of natural number. That means any natural number that we pick up, the statement p of n, which is given by this particular equation, this particular statement is going to be true. So here we have successfully used the principle of mathematical induction to verify our problem.